Okay, so yeah, I gave this talk. Oh, I've been given this variations of this talk for quite a while. Rick Dove, who actually was also on another PhD committee with another recent PhD graduate from Stevens, heard this talk and said, would I give it again? So this is an updated version from what he heard, but we've been doing this task for quite a while. We started with NavAir back in 2013, about September 2013, and I'll give you some historical perspectives on that. And so the way that we do this research is that it comes from sponsors like NavAir and other government agencies, and it goes through OSD, Office of Undersecretary of Defense, and so we get research tasks. So you can see I've had a number of research tasks, and I'm currently working on the latest two, which is 168 and 170 for the Army and the Navy, doing similar things. And so here are some of my, the institutes that I work with and some of the key contributors to the research. As you can see, I have a lot of other people that are in our collaborator network. They're all schools that are part of the Systems Engineering Research Center, which is it's a UARC, so there's about 25 universities, and as the question was there, yes, Dr. Dinesh Verma, he was the dean of the School of Systems and Enterprises, but he is also still the executive director. He's the principal investigator for this overall CERC. So a lot of this work involves a lot of people. Okay, so from an outline today, what I'm going to do is I want to go back to from a historical perspective to give you a little bit of context of how we started this work, and then pretty fast I'll try to give a statement of well, where we are, and then I want to go into covering what the research thrusts are now, given the context of what we had done in the past, and I give that some perspectives on what was my current research task, RT-157. It just ended, and there's actually a final technical report on either my website, markblackburn.com, or on the CERC site. You can find it either place and download. So all these research, these reports are all open to public, so you can definitely read them. And then I'm going to give you just another perspective from the Army's point of view, and we're working with Picatinny Arsenal. They do armaments, and then some conclusions, acknowledgments, and I use some pictures in here, but I put the credits in the back. All right, so the original question that was posed by our NavAir sponsor, and this is back as far as September 13th, is it takes too long to produce a large-scale air vehicle like the Joint Strike Fighter. Clearly, it's been taking, first flight was back in 2006, and we're just looking to get an operational vehicle. So it just takes a very, very long time for those things to roll out. And so the question was, is it technically feasible? And technically feasible was an important thing, to have a radical transformation. And then at that time they were saying model-based systems engineering. We've changed it to model-centric, and I'll explain why in a minute. But to achieve a 25% reduction in the time to actually develop these vehicles, and the key concept was using computer digital models. And as we proceeded along, we also got this other corollary that was really added, which was that, okay, things were looking pretty good about, what was really happening. But then he said, well, we want to also address this other thing, and that is that if we're going to use a lot of modeling and simulation, maybe to assess performance kind of capabilities, or to use finite element analysis, and those things are not really integrated together. It's do we have the need, and he used the word, our sponsor Dave Cohen used the word integrity, and that is that can we really trust the predictions of those models? And so his vision was that we would have this cross-domain multi-physics model integration, continuous refinement of these models through multidisciplinary analysis, supporting virtual V&V. He was talking about basically going back and forth across the traditional V, and actually doing everything from concept of operations, ConOps, all the way to manufacturing and even training systems. So you can see that it's the vision was pretty broad. And then actually, as we continue on, we also talked about and basically have a digital systems model that is basically, quote, the single source of technical truth. So what we did, and Sandy and Labs was actually one of our, Divinia was actually get this together. But we went out and talked to over 30 organizations, had basically face-to-face meetings, often as long as an entire day in length. And we basically just asked a very simple question. Just tell us about the most advanced and holistic approach to model-based systems engineering. We didn't really care what the name was, because when we started going out and talking to these individuals, they said, oh, you mean model-based engineering, or integrated model-centric engineering, which is what NASA JPL uses, or our MIT collaborators are using interactive model-centric engineering, or model-driven development, or model-driven enterprise, and so there's many different ones. And even another one of my students, Tim West, basically in an INCOSE Insight, I guess, actually used this word, which is this digital thread, which envisions the framework that merges physics-based models generated by cross-domain, discipline engineers during the design process with the overarching MBSE conceptual models on top. And so we say yes. Now, all those things are true. And so what's the underlying theme about it, and why people were talking about more model-centric, is there's this underlying nature of a huge amount of computational capability that's going on all at the same time. So we, in our report, because there was no one definition, and although we did actually produce a lexicon of over 700 items, and that's also available to look at on everything modeled, there was no definition, but so we just characterized it as the goal of integrating these different model types with simulations, surrogates, other systems and components at different levels of abstraction, fidelity, across those disciplines throughout the life cycle, with manufacturability constraints kept in mind. And since we had started with this, Mr. Welby, who was actually, he's moved up a level, he actually, in our CERC sponsor review in 2014, actually started using the words digital engineering, and that's actually what OSD is actually using today more than, and I mean, some people are just saying, well, we're basically confusing the whole thing is by just actually using the word model-based. So it's like they just wanted to get away from that, and they're just talking about digital engineering in general. So the one thing is true about NavAir, and I know this is an eye chart, now I'm not going to actually go through this whole thing, is that they're really big on evidence. So we did a lot of collection of evidence from various different kinds of things. I basically used basically a Bayesian model to try to characterize all the subjective information and sort of in some ways come up with a stochastic way to make the argument that we really have enough evidence that we are able to make the argument that yes, that we believe that it's feasible, technically feasible, not necessarily dealing with all the human aspects of it, but technically feasible. And then basically over 180 pages of narrative from every one of those meetings that we have. And a lot of this, especially for the industry, I was under NDA, or proprietary information agreement. And so those particular ways of showing the management, the senior leadership, they weren't working. So what we did is that we tried to just take a list of, and this is a non-exclusive list of all the topics that we actually heard from, modeling COT-ops to modeling patterns to multi-physics, modeling and simulation, multidisciplinary analysis and optimization, but to affordability, analysis, quantifications of margins and uncertainty, something that came from Sandia National Labs. And what we did is if we heard someone, talk about it or show demonstrations, even if we believed that they would actually, doing something that's related to this practice, we wouldn't count that. So yeah, ABC are like industry things, but if we saw it or actually they discussed it exactly, then we gave them an X, a check mark for it, to try to show that there was a lot of coverage in the aggregate. And that was what we were really trying to do, to argue in the aggregate that this is possible. And then there's another dimensionality that Dave Cohen was using, which was looking at it from a performance point of view. And so if a particular element here was related to performance or integrity or affordability or risk or methodological processes, which are in some ways you'll hear about a little bit, are really important, and or are addressing single source of truth, and also possibly addressing these other kinds of phased kinds of things that would occur that was at Dave Cohen's kickoff meeting. So that's what we did. In the aggregate, we argued that it was possible. And so what we came back with is that various organizations showed us their integrated environments and everything that they actually had. And so what we tried to do in our reports is I just created this, I call it, conceptual reference model or a canonical reference model of what went on. And so the key notion is that there's going to be appropriate views for various stakeholders. Some of them will use these rich modeling views, modeling and simulation views. But a lot of them will possibly be, subject matter experts that may be looking at analyses that actually are derived from a lot of these modeling things, and will be in now, very rich web interfaces. And so, and that information will be stored, in a single source of truth, integrated. That's ideally. And so, for example, some of the concepts that we even heard about, which was, say, NASA JPL, they use their open MBEE environment where they can actually look at a particular set of parametric information that was derived from, with analysis from something that was a much more rich modeling environment, and they can actually change the subject matter experts say, oh, no, that's not the right value of, say, like weight for this particular component, and they can change it, and it would end up propagating through basically automated workflows that basically understand the cross-domain implications of analysis. And when I use the word cross-domain, I'll go back to a simple example of multi-domain kinds of things that I think about because I work on aircraft vehicles. But we're working on this refueler UAV, unmanned aircraft, okay? And so and it's going to be a refueler, so it's got a fuel tank. So think about the valve out at the end of the pipe, okay, that basically connects to the fuel pump. So that's in the domain, that electrical valve is in the domain of the mechanical space. But it's also controlled electronically, so therefore there's relationships in the electronic domain to control it. But that particular electronic domain is also coupled to, say, the communication domain, remote communication, who's really controlling whether it's on or off. So there's in the communication domain. Or then there's also maybe in the fire control. So in other words, it would be an automatic shutoff. So all of those are types of things. So if that valve changed at any one of those places, we would want to actually know whether we potentially needed to rerun analysis across things. So that's sort of the concept. And so multidisciplinary analysis and optimization is a way to actually hook basically workflow, create workflows for solving and looking at parametric kinds of things that can bring in, performance or integrity or scheduling or even reliability kind of models, and basically sharing and keeping around knowledge, okay, reference models of things that had been done in the past, and then being able to actually use surrogates and other types of things using high performance kind of computing. And so that was sort of like the conceptual view that we actually had, but it even goes further, and that is that thinking about some of the future kinds of stuff that we've actually heard about in terms of AI and computer augmentation, which is, if you think about, say, the Grand Chess Master that was actually finally beaten by, I guess it was Big Blue, the computer. Well, what they did is that IBM created even faster machines. They actually didn't bring in the Grand Master, but they used, very good chess players, but when they were supplemented with, computer systems that would help them in, from a computer augmentation point of view, they're even able to beat more powerful computing systems. So that's the notion of beginning to understand even what we're trying to do, and obviously deep learning and machine learning can potentially be part of all of that. So what came away from our first go around was all right, what are now the main problems that we saw that are still needing to be addressed? And these are, I believe, are still true today. I just came back from the NASA JPL workshop and symposium a week ago, and these topics came up a lot. Cross-domain model integration. Okay, there's basically a lot of tools out there. They're often federated. They're not necessarily tied together, and tool-to-tool integration probably isn't necessarily going to work. There's also the model integrity. How do we understand, the prediction capabilities? And clearly, there's methods such as, quantifications of margin and uncertainty, which the people at Sandia know very well. And then there's modeling methodology. So one of the projects that we heard that's the perfect case, and it's documented, is, say, the DARPA Meta project. And they did a lot of things where they basically had an entire set of libraries, and they would more dynamically, select components from the library to actually try to assemble into a particular system through modeling and simulation. And what they came to find near, a good time to the process was that the actual component libraries were not modeled with the appropriate method that would actually allow the tools to enable their automation. And so methods are very, very important. And then the last one, we wanted to have a roadmap, but not just a technology roadmap. For example, the engineered resilience systems people have a technical roadmap, but we were looking at it for actually rolling this kind of thing out, which is, basically bringing out, the right methodologies, rules, of producing the artifacts given the new technologies that we had, and that would require, new competencies for the people that we're working with, and actually an operational paradigm change for actually how government and industry are actually working together, and then new governance for like how they would actually lead with that. So these are all things that are, still currently in our purview. So the bottom line, up front was that once we said all that, is that we knew that organizations, with a few exceptions, were really unwilling to share the quantitative data. And actually, our NAVAIR sponsor said, that's very interesting. So actually, since that time, they've been able to share a little bit more quantitative data. But in the aggregate, the qualitative data suggested that we could actually move on. So NAVAIR's leadership said, all right, we got to move out quickly because we got to keep pace with these industry organizations, especially since we're basically the lead system integrator, and we need to actually have effective oversight on people that are actually using these modern methods and tools. And then, so that was basically in around January of 2016, and then we got a change of command. And that change of command came in, and they just decided that they were going to accelerate the systems engineering transformation, which is how it's been branded right now. And so with that, I had this chart in the back of my slide deck for a long time, but things really changed. In a lot of ways, what we saw that we really need to have a different kind of coordination between government and industry, and that is we needed to do digital engineering in a very different way, and one in which is, in some ways represented by this picture, that they need to be actually working on these things and looking at it from a digital perspective together, and that is part of our big change. So as a result, Dave Cohen, our sponsor again, he came out with this framework that he thought that he could actually use, and this is about, I don't know, the 7th or 8th version of it. But the concept is that, think about it right down here, down the middle. So what he wants to do is on the left side, and I'll use his terms, during like the kill chain analysis, trying to figure out what platforms we're going to pull together. I have another picture of it in a minute to put it into perspective. Have industry begin to work with government, where the government is taking the lead on mission area models and simulation, and actually do a very iterative process where they basically come up with the key performance parameters that they want, mostly focused on performance, availability, and affordability, and all requirements are tradable, okay? But what they also want to do is that they wanted to actually represent the specification in models. And so when they actually, at this point in time, where they go to, say, send out the statement of work or in the request for proposal, what they want to do is that they want to put this model on, basically on contract. And what they want to do for source selection, okay, is to actually have the industry come back, elaborate that model. So, for example, you might think about it as being SysML models. It might have some degree of performance capability described as, KPPs for various different types of performance. An example for the UAV is, say, range is a key thing. And certain potentially, even aerodynamic or other kinds of things that they would actually put on. But then have at source selection almost be like a V&V effort of dynamic modeling and simulation coming back, where the contractors have elaborated that model, described how it taking it from, let's say, a functional logical perspective to actually adding additional details about specific design trades that they would actually have, cutting across, these areas here from vehicle to propulsion mission systems. And then once under a contract award, the government would actually work in a very different way. And Dave Cohen used the word with low impedance, that they would actually watch continuously. His idea is to get rid of the traditional kinds of gated milestones like, SRRs, system requirement review, system functional, PDR, CDR. Take those away, and what he's looking for is some type of a more of an objective means to continue to measure the design maturity as he watches risk and the uncertainty go essentially, uncertainty go to zero and risk go to zero. That's what he's actually looking for. Now notice that there's this a little bit of a challenge area here is that suppose that, for example, it's not achievable to actually meet the particular, say, key performance parameters. What he would potentially want to do is to actually come back and actually be able to, yes?
Sorry about that.
Okay, is to actually come back and potentially readdress the actual kill chains. In other words, rethink it. I mean, if you've actually thought about agile software development, I mean, sometimes what we do is that we basically say that we want these set of features put in there, but when we actually go decide of how long it's going to take or how much it's going to cost, it's like someone might say, well, I can get these features out, say, for example, in 6 weeks, but if you wanted that one, then it could take me like 10 months, but that's the same kind of thing. And in terms of like the threats are changing on us so quickly that they want the ability to do that. That's why they're believing that every requirement is now almost tradable. So that's the concept, so that they can get an initial integrated vehicle out very quickly. All right, so now that's his vision. That's what they're doing. That's what we're actually working on. We're actually having lots of different kinds of discussions with industry on how can we collaborate in a different way, and that includes intellectual property and data rights. And we also came away from the NASA JPL meeting where Kristen Baldwin actually did have the very first keynote address, recognizing that, look, maybe we've got the technical aspects of model-based, model-centric, model-based systems engineering down, or we know that it's actually happening, and there were so many presentations that we saw that actually talked about, yes, we know there's technical challenges, but we actually are doing it. And so therefore they've come to the recognition that they need to focus on model-based acquisition and actually potentially changing policy. And so that's what it's coming up with. But now let me just go through a little bit of what I said again. That was sort of like the bottom line. That's where we are. And but the idea is when we actually heard this is that they actually have this integrated warfighter capability. And when I said that they do come up with, say, kill chain analysis, and what they're trying to do is that they actually have advanced modeling and simulation at the mission level, but what they're beginning to recognize is that, while they look at cutting across, say, platforms to support surveillance, detection, tracking, and launch, is that what they might do is that they might look at different solutions than they've ever done before from a system of systems point of view, depending on, say, the timing and the threat. So in other words, they may decide to actually try to use sensors or targeting from a different platform temporarily if it's going to take too long for it to come out in the other way. All right. So, and now we're beginning to actually use what's called study views in this missionary simulation kind of capabilities, where the capabilities in there are, for example, things that you might find in terms of, say, their AGI system toolkit. I guess that was called a space toolkit or something. But what they're doing is that they're trying to formalize and leverage modeling and simulation of the what's called the JSIDs, the Joint Capability Integration. And so that's beginning to happen, and this is where we're starting at a very high level at the mission and beginning to move into the systems capabilities. So these same models and simulation that were used over in, say, the mission area analysis, now we're coming down to multidisciplinary analysis and optimization. So what we do is, and I'll show another example of this, where we build a workflow, but within those workflow, basically they're linking together different kind of parametric-based solvers for things that might actually be represented in the higher level, but they're the same kinds of things. So, for example, what would be a concern here? Well, let's just go to, for example, say the Joint Strike Fighter. I mean, they originally, I guess, were going to have titanium bulkheads. Now they actually decided to have aluminum bulkheads, and they actually cracked. And so that's a structural kind of thing. But so when they actually say that, well, I need to go make them titanium, now it affects weight. Well, with affecting weight, does it change the engines? Does it change propulsion? Does it change the aerodynamic shape? If it changes the aerodynamic shape, does it affect the way that the sensors work? These are the different kinds of multidisciplinary analysis kind of things that we want to be able to do. And we were able to go from, studying trades there in the tens to into the thousands. And even with, ERS, they're talking about doing, millions or tens of millions. That's the engineered resilience folks that work for Jeff Holland out in Vicksburg. So we're able to move much more quickly and actually drive it through a more systematic design of experiments. But now here's where part of the gap is. Okay, so while we might have a lot of MBE, and we don't have necessarily all those things as being cross-domain integrated, one of the other challenging areas is actually the overlay of what I would consider to be the architectural system models. When you think of, say, like, for example, SysML is a model-based systems engineering language that would be used, there is still yet some kind of disconnect, and so therefore there's lots of opportunity for us to actually improve there. So that's another area. Again, then I was talking about the notion of what we're looking for is to actually have a cross-domain methods that are in some ways tool agnostic. And a particular approach that we've been talking about is the use of ontologies, but not ontologies for ontology's sake, maybe domain ontologies, but also with the domains or with semantic web technology. And so why would we want that? Well, it turns out the ontologies provide a means for characterizing, say, information models about a specific domain. And as I was giving the example before, so, in the mechanical domain, you see you basically have valves and pipes and things. In the electrical domain, you basically can still see that you actually have electrical controls that are related to those valves, but they're looking differently, and they're different from different perspectives. And so, and the current problem is that when we go to a specific program, we're going to need a certain set of tools, and while some tools may actually be integrated, they're probably not all. And so we believe that we're seeing things, and this again was discussed in at least one keynote address and 2 workouts, briefings, that looking at alternative ways of using data interoperability as a means for actually achieving tool integration might also be an approach that makes it a little bit more tool agnostic. But now when you have an ontology too, okay, so an ontology in reality for some people, it just really looks like a schema. But in some ways, it's an evolvable schema. So in other words, if 10 years ago I just had a valve, okay, that actually represented the kinds of properties valves would have, but in today's world, now I actually have software-controlled valves. So therefore, you can evolve the ontology, be sort of upwards compatible. But now the semantic web technology also brings in a lot of the computational parts of the automation to actually reason about, is the information that's actually presented compliant with the ontology, and are there cross-domain relationships compliant? And so that's what we're really looking to actually do. And so therefore, how to do that really requires a lot of methodological guidance. And then the last one is that if we actually do a lot of these kinds of things in models, we basically can actually leave a lot of the manufacturability decisions potentially to very late in the game. And that idea was really, I don't know if it was started by the Toyota group, when they actually talked about, concurrent design or set-based design, but the idea is to actually leave your design alternatives open, a very long time, and then, so that's the idea. And we also heard a lot from organizations about actually doing modeling and simulation of the manufacturability of a particular system, and they can make a decision that, wow, this is like not very manufacturable, or the tooling would cost me a lot, so they basically keep the design trades from the space and back up and actually reconsider different alternatives, and that's a notion of step-based design. So for us, we're this upper box, we're this upper layer here, we're the research, and so one of the key things that was very exciting, I think, to say Kristen Baldwin and the Office of the Undersecretary of Defense, is that we're really taking this research that's been done with the CERC and actually rolling it out. And so we're really supporting, the new research, but also helping them understand implementation and how we can roll it out, and understanding the roadmaps along. And we have a number of different pilots that are going on to actually affect. And this is a very important thing. And it's like this word of the, a NavAir enterprise is truly enterprise. It's not only the systems that are designed, it's the designing system that needs to be created. And there was some very good talks too about showing organizations. I'll even just mention Airbus had a really great presentation, which is that information is downloadable about their entire environment. And it's people really are having environments that really are even are more elaborated on than the one that I gave you as the canonical reference architecture, but they are occurring. All right, so a little bit on our status. So yeah, so we're developing a surrogate UAV model. Okay, and what we want to be able to do is to do exactly what we said, roll that out. And our surrogate pilot is we're considering a couple of different organizations where we can do that and illustrate basically multidisciplinary analysis and optimization at the mission level kinds of trades, and at the system level. And then because NAVAIR currently was really mostly working in the DODAF environment, which was all they were normally concerned with is the communications path, they are realizing that now they're going to actually start working, and they're going to use SysML in this particular thing. So we actually had a UAV design, and as our team expanded, we basically turned it over to Georgia Tech, Russell Peak, and some of his researchers and his students, and they're working on elaborating this UAV model. And then we've also actually demonstrated the use of multidisciplinary analysis and optimization. Here's a particular example. So we basically had this workflow where we had the UAV geometries with weight, and then aerodynamics and propulsion and performance, and the key PPP, the key performance parameter on this one was actually range that we did. So we're just using this to demonstrate, but we also are using very high-end tools. I mean, I'm not trying to promote any particular tool. There's a number of different ones out there, but we wanted to ask research questions in the context of very high, high capability kind of tools. So we've got a number of licenses that are, academic kind of licenses, but then we want to look at, what are the key kinds of things from a methodological point of view of like how does one go about designing, workflow sequences? How many do we need? Which ones do we need? Then we look at the set of inputs and outputs, and do parametric analysis, and then actually do some dev experiments so we can actually understand sensitivities and visualizations that are related to those parameters before we go into full-scale optimization, where some of these solvers can take quite a while to actually use, and then use the appropriate, visualizations, say, to look at, different Pareto fronts and understanding the sensitivities of the things that really matter. And so another thing that's going on with another one of my PhD students, Tim West, again, that I talked about, which is he actually works at Arnold Air Force, or Arnold Engineering Center, and they run all the wind tunnels. And so he's looking to use Dakota, which is something that came from Sandia, along with the Create tools from the Engineer Resilience Systems people, and to try to come up with a better methodological approach to guide the use of this really limited resource of these wind tunnels. So they are, very, very large wind tunnels and small wind tunnels. So, and actually looking at computational things such as, CFD and, finite element analysis, see if we can optimize the different kinds of actually test methodology for actually carrying this out. Again, just as a, plug for my sponsor, or for my other team member, so that's Russell Peak. I was very interested myself in doing actually a lot of the ontological kind of work, but with all the stuff that came up, it's like I picked Mark Austin, who has actually been working in this area for maybe 12 or 13 years in the area of semantic web technology. So he and one of his PhD students are actually or a number of their PhD students are working in this area for us and looking at various different kinds of things, from using natural language processing to for requirements, to ontologies for requirements, and working on those specific things to actually demonstrate how that can be done. The last perspective is my Army ARDX sponsors. When we began talking with them, it was about a year ago, and we basically proposed something very similar, which was that they're looking at a framework, they're looking at their integrated development environment, and they want to understand the requirements given what they need to produce. They too basically have their own domains of interest, and so we're looking at a one that's actually tailored to theirs. Methods, again, for basically the same exact reasons, and they're doing it in the form of challenge areas. So while NAVAIR is coming at it from a very top-down point of view, leadership point of view, ARDX is coming at it from, in some ways, a bottom-up point of view. So they basically had the challenge area of counter UAS. In other words, how do they stop, say, UAS systems from what they do? So they had 3 challenge areas. They've actually expanded to 5, but one is looking at it more of the systems performance, CAD and those physics kind of stuff, with some multidisciplinary analysis and optimization. Challenge area 2 sort of overlaps in terms of operational scenarios, gaming technologies, mission trades, and using gaming technologies in that area, and then bringing it all together with an underlying information model to actually look at how it all can be pulled together. And to put that into perspective, it looks in some ways like this. So challenge area here, so if you actually think about the traditional things that you actually do, which is, so I have concept of operations, which they're doing through gaming technology, that might actually factor into like your requirements, what you really want to produce, that actually then actually has many hows, the designs of which you have, and then many more how wells, which is a lot of the kind of analyses that might be done. But as we said, it's like what ends up happening is the information from these, they may not be connected. So what we're really interested in is coming up with a way to actually understand, say, for example, and I use the word meta model, the information or the metadata from each of these various things that actually are done and actually how they're related together. And they actually have a very interesting decision framework. I know it sounds ubiquitous, but it's a very, and I don't think that I was able to put this, I didn't put it in here because I didn't have permission to actually put that slide in there. Very, very nice way to actually look at the kind of trade. So they can look at the life cycle cost of a particular candidate design against its actual value, and also look at it in terms of like the risk and uncertainty of actually producing it within a certain time frame. And so that was done by Dr. Matt Chili, who also is a Stevens graduate, and they have a tool that basically implements it. So there's a meta model associated with that particular tool, and we believe, and we're trying to work on it, that we can use the information that's collected along the way to basically populate that tool to a more systematically generate representations that in some ways become a methodological approach to actually guiding the key performance parameter inputs. So in other words, we actually have a bidirectional approach that I think that we could pay off. And so we have, and then Unity and VTMOC and distributed high-level architecture simulation. Those are just the kinds of things that we're actually using at the mission area simulation that are described here, represented. So that team, again, it's a very big team, but what we did is we laid out the research exactly that. So we have USC, who actually has their gaming technology. They work on, for example, the early synthetic prototyping with basically we're using Unity platform for researching graphical ConOps. We want to understand the meta model of information that's produced, both from an information model point of view, ontology underlying it, but also how it would feed and what information feeds to mission area analysis and then system area simulations. And then how does that feed and populate the parametrics that are needed to actually do multidisciplinary analysis and optimization? And how does that actually feed to a system model, which might be, say, something like SysML, and or actually relate to actually the model-based engineering, which is much more of the discipline-specific kinds of parts. So, and then how that all fits into, say, an information model. So you can see all these links are showing how these use cases, and yeah, we are actually using SysML to actually sort of model what we're doing for each one of these actually research use cases, and this just actually shows the stakeholders and the interrelationships between those tasks. So in conclusion, I think I'm finishing up in a pretty good amount of time here. So we basically, are evolving a framework and a new collaborative, operational paradigm. Basically, we're still conducting additional meetings. We have a number of them coming up with industry to go out and look at that concept that I talked about before from Dave Cohen. We have, various different pilots going on. Workforce development is basically a key thing. We have a number of different training things going on right now and pilots to try to use a few people from the outside, with the small number of people that NAVRA would like to use to organically grow these kinds of things. But we also are looking at it as how do we actually do contracting? What would source selection look like? And what is the new objective criteria that we can use for trying to understand or assess the maturity of something, versus doing it the old traditional kind of ways with those monolithic reviews. And so policy might be an answer. I mean, we just heard Kristen Baldwin say maybe it's time to look at that. And so as I said, our worksheet, we have a lot of collaboration going on. The ARDEX stuff and the NAVAIR work, they are actually working together in this digital engineering strategy that's being headed by Philomena Zimmerman. Phil Zimmerman, some of you may know her. We also have brought in, and we're working with the Naval Postgraduate School, Dr. Kristen Gianmarco, who also is, from Stevens. They're actually working, we're actually working a number of different projects together. So this is under another one of these CERC research tasks. A lot of this is actually was stimulated, and all these, the relationships really were fostered by what we held as the Government Industry Forum back in May of this year, where we brought in government, industry, and academia and had a number of different sessions about this notion. Dave Dave Cohen got up and talked about doing it. There's a report on the CERC Talks website. I should have actually had it in here. I can actually let anybody know. And then we're also working with the Aerospace Industry Association. They actually created a white paper last year where I was involved. I was the only academic involved on doing better requirement engineering through model-based systems engineering. They created a white paper, and this year the idea or the actual problem is working on a ConOps for how industry and government can collaborate through MBSE or model-centric design. So this is really led mostly by industry to try to come up with how can we deal with some of these ideas like data rights and intellectual property. And then there's another set of people. There's some cross-domain stuff, and I'm also in this one in the NDIA working group on using digital engineering for competitive down select. So there's a lot of things going on there. It's not just technical, and there's a lot of things that are like I said, even sociological, I suppose, in some of these kinds of things. So there's just a number of things that we're doing. So yeah, there's so many people that we actually have, and that I need to thank, because obviously they've been working here, so I included those as acknowledgments. If I use too many acronyms, I hopefully put them in there, and my image credits are here. So thank you.